Semiautomatic methods. In this section, we present three methods to generate NPT that ease the burden for experts during the quantification process of a BN. These methods allow the construction of large-scale BN. The first is the RNM, which completely eliminates the need for direct probability assessment. The second is the WSA, which is based on two heuristics and needs only part of the NPT to be elicited from the expert. The third is an adaptation of the analytic hierarchy process, AHP, which reduces the cognitive effort, biases and inaccuracies from estimating probabilities to all combinations of states of multiple parents at a time. From now on, we will reference the latter as simply AHP. These three methods attack the magnitude problem of building NPT. N, the ranked nodes method, RNM, is presented. In this lecture, it is introduced the concept of ranked nodes, ordinal random variables represented on a continuous scale ordered monotonically in the interval. For example, for the ordinal scale, low is represented by the interval, medium, by the interval, and high, by the interval. This concept is based on the doubly truncated normal, t-normal, distribution. A normal distribution is made of four parameters, mu, mean, i.e., central tendency, sigma 2, variance, i.e., uncertainty about the central tendency, a, the lower bound, i.e., 0, and b, upper bound, i.e., 1. With a normal distribution, it is possible to model a variety of curves, i.e., relationships, as a uniform distribution, achieved when sigma 2 equals, and highly skewed distributions, achieved when sigma 2 equals 0. N, we show an example of t-normal with same mu but different sigma 2. Examples of t-normal. In this method, mu is defined by a weighted function of the parent nodes. There are four function types: weighted mean, mean, 2, weighted minimum, min, 3, weighted maximum, max, 4, and a mix of both min and max functions, mix min max, 5. In practice, these functions define the central tendency of the child node for the combination of parent node states. The weight of each parent node, which quantifies the relative strength of the influences of the parents on the child node, must be defined by a constant W in which Wn. Fenton et al. Do not present the details to, in practice, implement the solution. Despite presenting the mixture functions, there is no information regarding the algorithms used to generate and mix t-normal, define sample size and define a conventional NPT given the calculated t-normals. The latter enables the integration of ranked nodes with other types of nodes such as Boolean and continuous, which brings more modeling flexibility. N, it is proposed a probabilistic algorithm for this purpose, composed of two main steps, I, generate samples for the parent nodes and, 2, construct the NPT. In step 2, for each possible combination of values for the parent nodes, i.e., each column of the NPT, the samples defined in the previous step are mixed given a function selected by the user and a t-normal is generated using the resulting mix and a variance defined by the user. An overview of the algorithm is shown in. Overview of the algorithm. As already mentioned, a ranked node is conceptually represented by an ordinal scale, which is mapped to the continuous interval. Thus, it is represented as a set of uniform distributions. For an ordinal scale with three values, for example, bad, moderate and good, U01 equals pad asterisk U01/3 moderate asterisk U1/32/3 could asterisk U2/31, where piece the density of the distribution. For the example shown in, the set of uniform distributions is composed of the union of three uniform distributions U01 equals 54.7 asterisk U01/336.5 asterisk U1/32/38.80 asterisk U2/31. Numerically, this union is calculated using samples. Considering a sample size of 10,000, to represent the NPT of the example shown in, it is necessary to collect 5,700 random samples from U01/3, 3,650 random samples from U1/32/3 and 880 random samples from U2/31. Conversion from ordinal to continuous scale shows that the algorithm is composed of four collections: repository, a vector to store the samples of base states for the parent nodes, parents, a vector to store references to the parent nodes of each child node, in which k is the number of parents, states m, a vector to store the states of each node, in which m is the number of possible values for the child node given the combination states of its parents, and distribution, a vector to store the resulting distribution for each possible combination of states of the parent nodes. The repository strategy is used for optimization purposes. First, it is registered in memory, i.e., in repository, distributions that represent the base states, which are states with hard evidence, i.e., a node has 100% of chance for a given state. For instance, for a node composed of the states, are registered samples for 100% bad, 100% moderate and 100% good, which respectively has mu equals 1/6, mu equals half and mu equals 5/6. For this purpose, samples from a uniform distribution with the limits defined given the thresholds of the scale are collected. For instance, for 100% good, it is collected samples of a uniform distribution limited in the interval. And it is empirically defined that using a sample size of 10,000 is enough to guarantee a margin of error less than 0.1%. Each sample is registered with metadata regarding its configuration, i.e., number of states and mu. The data in repository is used to generate samples for a node. Therefore, the samples for a base state are only generated once and reused later. The next step consists of, for each combination of the parent nodes, mix the normal using equidistant samples, randomly selected for each parent node. The samples are mixed using one of the given functions, for example, mean, min, max or mix min max, and the defined variance. To mix the distributions, a random element from each sample of the parents is removed and used to calculate a resulting element using a given function. For instance, consider node A with two parents B and C. If we are calculating the probabilities of A for the combination low, high in the selected function is mean with equal weights, if the values removed in an iteration were 0.1 and 0.7, the resulting value would be 0.4. This step must be repeated until the collections of samples are empty. Afterwards, the set of calculated elements and the given sigma are used as input to generate a normal. The resulting distribution is converted to an ordinal scale and represents a column in the NPT of the child node, i.e., in the given example, the column for the combination low, high. At the end of this step, all the possible combinations of states of the parent nodes are evaluated and the NPT for the child node is completed. Accordingly, the inputs to generate the NPT of a child node are, a weighted expression capable of generating curves equivalent to distributions expected by the experts, a set of weights of the parent nodes, and a value for sigma 2. To determine the weighted expression, one can ask the experts to assess the mode of the child node for different combinations of the extreme states of the parent nodes. For instance, let us consider the Bayesian network shown in along with the mode assessments of the experts in Table 1. Mode assessments for teamwork, checkmarks indicate the mode assessment of the expert. First, let us consider the rows 1 and 4, where all the parent nodes are in the highest and lowest states respectively. As can be seen in Table 1, when all the parent nodes are in the lowest or highest states, the mode of the child node is also the lowest or highest state. Such a probability distribution can be obtained by any of the weighted expressions. Now, let us consider the row 1 as the initial state. Rows 2, 6 and 8 indicate that when the state of a single parent node shifts from lowest to highest state, the mode of the child node shifts towards the highest state. Similarly, consider row 4 as the initial state. Rows 3, 5 and 7 indicate that when the state of a single parent node shifts from highest to lowest state, the mode of the child node also shifts towards the lowest state. However, it is quite clear that the shift effect is stronger when it occurs from the lowest to highest state. Hence, Table 1 reveals that the mode of the child node is inclined to go more towards the highest and lowest states, which makes the max function more suitable to express the distribution expected by the experts. The process to determine the weights of the parent nodes and the variance parameter is not as straightforward as to determine the weighted expression. There is no guideline in the literature, as far as we know, to aid in this task. Nonetheless, one can use the mode assessments in Table 1 as a starting point to define the weight of the parent nodes. For instance, considering max is the most suitable function to express the probability distribution, let us examine the rows in which the states shift from lowest to highest in Table 1. Finally, let us consider row 1 as the initial state. Rows 2, 6 and 8 indicate that the parent nodes have different strengths of influence on the child node. That is, when the parent node autonomy shifts from lowest to highest state, the mode of teamwork slightly shifts towards highest states. However, the shift is higher when the state changes in the parent node collaboration, as can be seen, if one compares rows 2 and 6. A similar effect is observed when comparing rows 6 and 8. Hence, it is derived from Table 1 the following constraint: autonomy weight.